Okay, good evening. So this is week 2. And it's Tuesday. So today's agenda, we are going to look into the extension of Euler's formula. Okay, and an important part to take note, output studies is important. You have to be able to, the major learning outcome is regarding the boundary conditions. A lot of times students have problems with this chapter is because of boundary condition. Okay. Before I go on, homework 01 will be available on May the 15th, and it will be due on, let me check, be due on May 22nd at 2359. Okay. Grades is based on completion. So if there's 5 questions, you have to complete doing all the 5 questions. We'll give you the grade, and then I'm not bothered whether is it right or wrong. As long as you do it, you get the grades. Okay, so it's based on completion. It's important that you do the homework, and important that you know the examples from the lectures, because that is where the questions for the term test will be coming out from. Okay, so the question for the term test will be coming out from the homework and the examples. I'll write this down. Okay, so term test question will be from the homework and examples given in lecture. Okay, not exactly the same, but similar. Okay, so if you do the homework and understand the example, you should be fine. Okay, right. So we are going to look into the extension of Euler's formula. Okay, we go. So Euler's formula for buckling is such that we have P critical is equal to pi squared EI over L squared, or you have critical stress is equal to pi squared E over L over R squared. Okay, so this is what we call the node, that the L over R is what we call slenderness ratio. Okay, so we are aware, right, that the resistance node, or the resistance to buckling is a function of is a function of Young's modulus. Is a function of length, cross-sectional area, which will affect your I, right, your second moment of area, and also how the structure is fixed at both ends, or is held at both ends. And last week we did pin. Okay, so we look at if we look at condition number 1, right? Okay, we look at condition number 1. We have it at both ends. Both ends are pinned. So if both ends are pinned, okay, so we are going to look into this diagram over here. Okay, both ends are pinned, and we have derived this before. Okay, we have looked at both ends are pinned before. So this is an example of both ends are pinned. So what is the difference? Okay, let me highlight what is the difference. Okay, so if we will have to have a general transformation, okay, if we were to have a general transformation, so this is my I'm going to call this my if this is my okay, I can call this my X and Y. Okay, and then we have our rotation about Z. Okay, so if we look at the structure over here, right, at point A, okay, so at point A, we know that X motion is equal to 0, right? Because it cannot move, okay, so no horizontal movement. Right? And for this case, y is not equal to 0. This is because you have you allow vertical movement. Okay. And then if we look at moment about z at point A, it is equal to 0. Okay, so some of you might say, how do we know that's equal to 0? Like what I told you before, if you remove the support at point B, let's say we remove the support at point B, this beam can rotate left and right about the pin at A. Okay. So as you can see, point A is pinned. Point B is also pinned. And the moment resistance at point A is equal to 0. Another way to look at it is if we were to draw a neutral axis. Okay. When we draw a neutral axis between the 2 points. Okay. And what you realize at point A, the structure at point A, let's say at point A, and if you look at the slope, okay, if you look at the slope at point A, there's a slope at this orientation, right? Point A. So as long as there's a slope, there's a theta down here, right? So theta is not equal to 0, right? So when this is the case, when theta, right, properly, when theta is not equal to 0, mz is equal to 0. Okay. So we look at point B now. So at point B, we realize that x is equal to 0, y is equal to 0, right? So moment about z is also equal to 0, right? Why is that? Again, if I were to draw a line, a tangent at to point B, right, looking like this, you have an angle over here known as theta. So when that's the case, moment is equal to 0. Okay. So when that's the case, I want you to focus this term over here, right? So when both ends are pinned, right, with both ends pinned, right, LE, the equivalent length, is equal to L. Okay, the equivalent length equals to L. So therefore, so what does this actually mean? This means, right, if we look at the general formula for buckling, right, we know that the critical load is equal to pi squared EI over, by right, this should be known as LE squared. Okay, LE is equivalent length. Likewise, this will be equal to stress critical is equal to pi squared E bracket LE over R squared. Okay, so for both ends pinned, right, we know that the stress critical is equal to pi squared EI over L squared, and the critical stress is equal to pi squared E. So what we did is we replaced LE by L. Okay, because we both ends pinned, LE is equal to L. So I remember sketching this last week, right? So what does this actually means? And I'm going to quickly recall. So remember last week, if we I've highlight that if we have a critical stress of equal to 250 times 10 to the power 6 Pascal, and then we have a Young's modulus of equal to 200 times 10 to the power 9 Pascal, and then for this case, our LE is equal to L, okay, because we have both ends pins. Okay, both ends pin. So when we calculate that we apply the formula where we are stress critical is equal to pi squared E over L over R squared.